Let's prove that the area under the Gaussian curve is the square root of pi. We're going to show that this area is the square root of pi, or equivalently, that the integral from minus infinity to infinity of e to the minus x squared dx is the square root of pi. Equivalently, the square of this integral must be pi, so let's prove that. Now, this square is a product of this integral with itself, and here x is what we call a dummy variable. So I'm going to write one of the factors with the variable in x, and then the other factor, I'm going to change the variable for fun and just call it y. Now, before I go on, one really has to prove that this integral converges, so that this is an actual real number. I'm not going to do that. Let's assume that this does converge, is a number. Then if this is a constant, I can bring it inside this integral as a constant. So now I have the integral with respect to y, and then this number as a constant in front. But now this is some sort of constant with respect to x, so I can bring it multiplying inside this other integral, and I get this integral in the inside, but e to the minus x squared times e to the minus y squared is e to the minus x squared plus y squared quantity, so that product we have reinterpreted as a double integral. So the upshot is that the square of the integral I want is actually this double integral, but this function, as a function in two variables, has a radial symmetry which screams for a change of variables to polar coordinates. So we're going to change to polar, with the new variables being the angle theta and the radius rho. And now we do the change of variables in the integral, x squared plus y squared, that is rho squared. So I get an e to the minus rho squared. And dx dy, when I do the change of variables in the measure, I get what's called the Jacobian of the transformation, which is rho in this case. So dx dy becomes rho d theta d rho. So this double integral in x and y has become this double integral in polar coordinates. So now we can start integrating. This function here is constant with respect to theta, so the integral inside is easy. It's just 2 pi times the function. Now, this is an improper integral, so we have to put a limit as r goes to infinity, integral from 0 to r of this function. But this integral is also easy because it's an immediate integral. If you do a u substitution with u equals rho squared, then you find that the integral or an antiderivative of this function is just that function. Therefore, this integral becomes minus pi times e to the minus r squared plus pi, and as r goes to infinity, the limit is pi.